Good morning all. Today we will cover folding transformation. Now folding transformation is the process which reduces the area of integrated circuit by reducing the number of functional units. Means only by reducing the functional units we can reduce the area of the integrated circuit, and it is done by the folding transformation. And how it is achieved? This can be achieved by multiple algorithms are time multiplexed on a single functional unit. This will decrease the area but at the cost of decrease in speed. Okay. Now let us consider a DSP system. Now in this DSP system there are n number of adders and n number of multipliers. Now 1 unit time is equals to 1 computation time. Now there are n number of adders and n number of multipliers. So how much time is needed? N unit time is needed. And the folding factor for this DSP system is n. And t iteration is equals to 1 unit time. Now let us consider a simple DSP program. Y of n is equals to a of n plus b of n plus c of n. Now here we require two adders to add a plus b and b plus c. Now here this is first adder and this is second adder, a1 a0. Now this first adder will be having two inputs, that is a of n and b of n. At the output here we will be getting a of n plus b of n, and it gives to the input of second adder, and the output of this adder is y of n is equals to a of n plus b of n, which is here, plus c of n. C of n is coming from here. Okay, now this is a simple DSP program. Critical path time is this adder will require TA time and this adder will require again a TA time. So critical path time is TA plus TA is equals to 2TA. Here T sample is equals to T iteration and it is equals to 2TA. Here the input will give at the time of t, and here we will be getting output at t plus 2TA time period. Now using pipelining we can insert a delay element in between two adders. If we use a pipelining, then here we have to add one delay element in between of these two adders. So this is the pipelining system of above simple DSP system or simple DSP program can be implemented by using a pipelining process. Simply here in between of two adders, here we have added one delay element. Okay, now there is no difference or as the input in previous circuit the input were an plus bn. In this circuit also the inputs are an plus bn, but here there is a difference between previous and this current circuit, as the delay element is inserted here. So at this adder we will be getting this an and bn after 1 unit delay time. Okay, and here c of n, instead of c of n here it is c of n minus 1. Therefore y of n is equals to a of n minus 1 plus b of n minus 1 plus c of n minus 1, and y of n plus 1 is equals to a of n minus 1 plus 1. Minus 1 plus 1 get cancelled, so it is a of n plus b of n plus c of n, and y of n plus 2 is equals to a of n plus 1 plus b of n plus 1 plus c of n plus 1, and critical path time is TA, and T sample is equals to T iteration is equals to TA. As this we have seen earlier, x of n is given at t time and y of n minus 1 will be getting at t plus TA. Okay, by adding extra register you can reduce critical path time as well as sampling time and iteration time. How? We'll see that. This is pipeline DSP system. This is adder A0, adder A1, AN, BN are the input of this first adder, and here the adder 1 is having the input is C of N. Now T clock. T clock is given at the input of this delay element. Critical path time is TA. T sample is equals to T iteration is equals to TA. Therefore, T clock is equals to TA. This is the clock time. This is your one clock cycle, and this is second clock cycle. The first clock cycle is TA, second clock cycle is TA. Okay. Now let us have TA is equals to 1 unit time. This TA is equals to 1 unit time. So T sample is equals to T iteration. It is equals to 1 clock cycle. So TA is equals to 1 clock cycle. Now in kth cycle, A0 is equals to AK plus BK. At kth cycle, A0, this A0 here, it is equals to AK plus BK. Similarly, A1 is equals to AK plus BK plus not AK, A1 is equals to AK minus 1 plus BK minus 1 plus CK minus 1. Why it is minus 1? Because of this delay element. And at K plus 1 cycle, A0 is equals to A K plus 1 plus B K plus 1. Simply plus 1 is getting added here, and A1 is equals to AK plus BK plus CK. Okay, now for reducing number of adders, go for folding technique. Now if we want to reduce the number of adders, okay, we have to go for the folding technique. Now see here, instead of using 2 adders, here we can reduce this 2 adder to 1 adder. Okay, so that the computation time will reduced. Okay, and speed will also get increased. So here we will go for the folding technique. Okay, now for that folding technique, here this is 1 adder, 2 adders are reduced by 1 adder. Okay, this is the clock cycle, this is TA cycle. Now here you can see AN and BN are the input and CN is the input of this A1. So at 0th clock cycle or TA clock cycle, A0, B0 are getting added. Okay, and then C0 will get added here. So for that, here we have to go for a multiplexer. Here we are using this multiplexer, and the input of this multiplexer is AN at 0th clock cycle, and here input is BN at 0th clock cycle. So A0, B0 will get added, and then it gives to the delay element. So the output of delay element is A0 plus B0, and then this gives at the output of delay element will feedback and give at the input of this multiplexer, and at first clock cycle we'll get A0 plus B0 plus this C0. Okay, at second clock cycle or 0th clock cycle, and this is first clock cycle if we say. So how much computation time is required here? The computation time is 2 TA. It means 2 clock cycle. And how much is N? N is the folding factor, and N is equals to 2 here. So this is all about the folding technique in short. Now in next lecture we will continue